So the next speaker is Zi Guan. She will talk about untangling the security of Killian's protocol, upper and lower bounds.
Thank you for the introduction. So this is a joint work with my advisor, Ale, and amazing Marcel, Nick, and Alon. Ale is also amazing. So the good thing about starting the talk as the last one in this session is I don't have to go through too many definitions. So I think we've seen interactive proofs a lot of times. It's a proof system, it has prover verifier, they interact, and we have the usual completeness and soundness notion. And here, since it's a proof system, the soundness is against all kinds of adversaries, including the possibly unbounded ones. And one very basic but important efficiency metric that we care about for interactive proofs is the communication complexity. Unfortunately, in the more than 30 years ago, it was proven that for hard languages, like NP complete languages, we cannot have interactive proofs whose communication complexity is small, which is way less than the witness size for the NP. So this makes people start to be very interested in studying whether it's possible to get around with these limitations, thus start to look at interactive arguments, which is essentially interactive proofs with computational soundness. And computational soundness, which was already mentioned before as well, is just soundness, but against time-bounded adversaries. Most of the cases, poly-time-bounded adversary. And it's a relaxation on the soundness arrow that we just saw from the previous slides. And the good thing is that now we don't have the same limitation anymore. And what is amazing about interactive arguments is that we can actually construct explicitly interactive arguments for NP whose communication complexity is very, very small. And we call those interactive arguments the succinct interactive arguments. And in this work, we also consider another relaxation where we consider soundness arrow against adversaries whose expected running time is bounded. And we put a little star on the arrow and time bound to represent expected time. So now, like, why do we care about interactive arguments other than the fact that it's amazing, fundamental, and simple? It exists only assuming simple cryptography like collision-resistant hash function. Nevertheless, the possible savings we have in the communication complexity and sometimes also verification time is super, super useful in places like zero knowledge with non-black box simulation, malicious MPC, and also, very importantly, it's often a stepping stone towards succinct non-interactive arguments, which we usually call snarks. It was proven that we cannot get snarks for hard languages from falsifiable assumptions. Therefore, it's often the case that people get snarks by combining interactive arguments with non-falsifiable assumptions or some idealized models. And among them, Killian's protocol is the first and simplest construction of succinct interactive argument. So let's look at what is Killian's protocol. It has two very basic building blocks. The first one is probabilistic checkable proof, which is a proof system where the verifier uses R bits of randomness to query Q locations of the oracle string sent by the prover. And the other one is a vector commitment scheme, which is a nice abstraction for succinct commitment scheme with local openings, such as Merkle tree. VC scheme has two phases. The commit phase, which you take a message and commit to it. And also an open phase, which you start with a query set, get the answers corresponding to your message that you commit, and get an opening proof from the scheme. And it is guaranteed that if the answers are honestly generated, then you would pass some check associated with the VC scheme. The security notion we care about for vector commitment scheme is position binding, which is saying that consider an adversary that provide me with 2 query sets and 2 answers for one single commitment scheme, the probability that the answers disagree with each other or there is a location that's inconsistent is upper bounded by epsilon VC. Killian's protocol is just ask the prover to commit to the PCP message pi, and the verifier sends a randomly sampled PCP randomness, and then the prover provides corresponding answers and opening proofs using the VC scheme. The fundamental question that we ask in this work is, what is the security of Killian's protocol? And now some of you might already notice that Killian's protocol was introduced in 1992, which is over 30 years ago. So there must be some security analysis, which is true. It's commonly believed that Killian's protocol is well understood, and in particular, when you start from good PCP and good VC scheme, you get a good argument with negligible soundness error. And in Killian's original work, he actually gives an informal analysis. And then later, Barak and Goldrack proves that gives a formal analysis of Killian's protocol with the caveat that there is some non-trivial restrictions on the underlying PCP. And moreover, their analysis has a multiplicative constant factor in front of PCP, which shouldn't exist. So it's kind of surprising that Killian's protocol has been around for a long time and is widely used, but it doesn't have a formal security analysis in the general case. So before I get into what we prove for Killian's protocol, I want to take a slight detour to talk about another protocol that share a very similar structure as Killian, the Schnorr identification scheme. I think Sigma protocol was also introduced in one of the earlier talk, and they do look similar. It's like a 3-message protocol, and the difference is that Sigma protocol has special soundness. And there are actually numerous works studying security of Schnorr's protocol in different settings. But however, unfortunately, there are still gaps and very challenging open questions remaining in the field of understanding the security of Schnorr's protocol. So now I should have planted the question in the audience, why am I talking about Schnorr's protocol? One of our contributions is actually to show that proving the security of Killian's protocol is no easier than proving the security of Schnorr's protocol. And this actually leads us to wonder whether Killian's protocol is actually well understood. And moreover, we do have a general and the current tightest analysis of Killian's protocol, but similar to the situation with Schnorr's protocol, there are still very interesting open questions and barriers in our understanding of the security of Killian's protocol. So formally, what did we show? In terms of upper bound, let's consider a PCP, a VC scheme, compile it using Killian's protocol. And what we get that is that for every instance not in the language and some error parameter, an arbitrary one that we can set, epsilon greater than 0, it is the case that the security of Killian is upper bounded by security of PCP plus the security of VC plus an additive overhead on the epsilon. And what is important is the TVC parameter, the size of the VC adversary, which in this case we show is that it is T arg times an overhead of L over epsilon, where L is the proof length of the PCP. And similarly, in the expected time setting, we show an almost identical bound, except that now our overhead in the VC adversary running time, expected running time, has an exponential improvement. So instead of L over epsilon, it becomes log of Q over epsilon, where Q is the query complexity, which is trivially upper bounded by the proof length of the PCP. And moreover, we have lower bounds. And as mentioned before, we show that Killian is as hard, at least as hard as Schnorr. And in particular, we show that there exists a certain PCP and a vector commitment scheme such that for every instance not in the language, the soundness error of Kilian's protocol is upper bounded by that of Schnorr identification scheme. And a similar bound was also proven for the expected time setting. So let's look at what are those bounds and actually how tight they are. So in the strict time setting, if we take a reasonable bound for the discrete log problem, what we get for Schnorr and what we get for Kilian is like that. And it's not hard to see that there is actually a polynomial gap that actually comes from this L over epsilon factor in this analysis in the strict time setting. So this remains an open problem, and personally I find it very interesting whether to show that whether we can actually close the gap or not. And in the expected time setting, it's better, the situation. So the best known analysis for Schnorr identification scheme in the expected time setting and the one for Kilian is almost tight except for a polylogarithmic gap. And that's everything. And I think that's not my latest slide, but I just want to mention that we have a recent follow-up on the quantum version of the similar work, but instead of PCP-based, we have an IOP-based. It's on arXiv. It's also with Nick, who is in the audience. So feel free to talk with us during coffee chat if you're interested. Thank you.
Thanks for the talk. I'm just a bit puzzled by, maybe you're aware of a quantum rewinding paper by Fermi Ma, Nick Spooner, and Alessandro Chiazza, Mark Zandri.
The breaking very first one.
The barrier, yeah, that one. And I wonder how that compare with your work, because also they claim to analyze Kilian's protocol. That's
that's a great question. So basically, in this earlier quantum work, they focus first on building the first quantum rewinding algorithm for Kilian, and the analysis there is actually for negligible regime. So they assume that the PCP and the VC have negligible error, and then show that Kilian has post-quantum soundness that's also negligible. And moreover, we kind of also add the emphasis on both the expected time setting and the lower bounds, and the connection to Schnorr and general sigma protocols. So that's basically the difference between the two works. Does that answer your question?
Yeah, probably. Thanks.
Okay.